Alright, let's look at relative extrema for a function. I remain your presenter, Dr. Okeke Ikena Stephen. In general, let's look at the relative and global extrema for a function. Let f of x be a function of x, which is defined for this interval x in the closed interval x1, x2. Then we have the following definitions. 1. If f of x minus f of a greater than 0 for all values of x in the total interval x in the closed interval x1, x2, except x equal to a, then the function has an absolute minimum at x equals to a. 2. If f of x minus f of a greater than 0 for all values of x except x equals to a in the subinterval x in the closed interval alpha, beta, containing x in a, then f of a is a relative minimum. That is, it is a minimum with respect to all other values of f of x for the particular subinterval. 3. Absolute and relative maxima are defined in a similar manner. Now let's look at this diagram that shows the different stationary points. This diagram has a closed interval x1, x2 and a subinterval containing alpha b and beta b. Now at this point A, B, C and D, we have that the extrema are f of A, f of B, f of C and f of D, as can be shown in the diagram here. The relative maxima and minima values of a function are called relative extrema. From the diagram above, the relative extrema are f of A, f of B, f of C, and f of D. F of B is a relative minimum for the interval x in a subinterval alpha b, beta b. The absolute maximum value of f occurs at x equals to a. The absolute minimum value of f occurs at x equals to d. In general, values of x at which the slope changes sign correspond to relative extrema. Next, methods for finding relative extrema for a continuous function. Method 1. Determine the values at which the first derivative vanishes. These points are called stationary or critical points. 2. Method 2. Test each stationary point to see if the slope changes sign. That is, if the second derivative is positive or negative, the stationary point or critical point is a relative minimum or maximum. That is, if the second derivative is positive, the critical point on the relative or the stationary point is a relative minimum. But if the second derivative is negative, the stationary point or critical point is a relative maximum. Note that if the second derivative also vanishes, we must consider higher derivatives at the stationary point in order to determine whether the slope actually changes sign. In this case, the third derivative must also vanish for the stationary point to be a relative extremum. Next, how do we investigate or find out relative minimum and maximum points with the differential calculus? Here, we shall involve differential calculus to investigate the relative minimum or maximum points. So let's define the the concept of relative maximum and relative minimum using differential calculus. A relative maximum point is a point where the function changes direction from increasing to decreasing, making that point a peak in a diagram or graph. Similarly, a relative minimum point is a point where the function changes direction from decreasing to increasing, making that point a bottom in the graph. Next, let's look at the examples. Example 1. Find the critical point of the function. F of x equals x raised to the power 3 over 3 minus x squared over 2 minus 6x minus 4. So at this point, we shall find the first derivative of this function with respect to x, and then equate it to 0, and then find the critical point of the function. F of x equals x cubed over 3 minus x squared over 2 minus 6x minus 4. Now these are the solution. So look at the function x cubed over 3 minus x squared over 2 minus 6x minus 4, and then find the first derivative. And the first derivative, we have the power, which is 3 times the coefficient, which is 1 over 3, then the power minus 1, we have 2. So in that case, differentiating x cubed over 3, we have x squared. Differentiating minus x squared over 2, we have minus x. Differentiating minus 6x to have minus 6. Differentiating minus 4 to have 0. Hence, the first derivative of f of x now becomes f prime of x equals x squared minus x minus 6. Now finding the critical point by equating this first derivative to 0, we have x squared minus x minus 6 equal to 0. Factoring out, we have x plus 3 times x minus 2, and then from there, setting to 0 to find the critical numbers. Therefore, x1 equals to minus 3 and x2 equals to 2. Example 2. Find out the relative extremum point of f of x equals x cubed plus 3x squared minus 9x plus 7. The same step, we find the first derivative of this function. And the first derivative is 3 times x raised to the power 3 minus 1 plus 2 times 3x 2 minus 1. Differentiating minus 9x to have minus 9. Differentiating 7 to have 0. Therefore, the first derivative of the function x cubed plus 3x squared minus 9x plus 7 gives 3x squared plus 6x minus 9. Then equating to 0, we have that the critical points are x equals to minus 3 and x equals to 1. So because we have these two critical points, we shall have 3 intervals. Interval 1, when x is less than minus 3. Interval 2, when x is between minus 3 and 1, minus 3 and 1 excluded. Interval 3, when x is greater than 1. For interval 1, x is less than minus 3, we pick an x value. For instance, minus 4 is less than minus 3, and then evaluating f prime of x at x equals minus 4 to have 15, and 15 is greater than 0. Hence, f is increasing at x equals minus 4. Interval 2. On interval 2, we have minus 3 is less than x, less than 1. Between minus 3 and 1, we pick an x value, which is 0, and 0 is between these minus 3 and 1. Evaluating f prime of x at x equal to 0, we have that f prime of 0 is minus 9, and minus 9 is less than 0. Hence, f is decreasing. Interval 3. X is greater than 1. Picking an x value, let's say 2. 2 is greater than 1. Evaluating f prime at 2, we have that f prime of 2 is 15, and 15 is greater than 0. Hence, f is increasing. Now, let's look at this critical point at x equals minus 3 before it was increasing, after it decreases. At x equals to 1, the function decreases, after that it increases. So at this point, the function has a maximum point at x equals to minus 3, and the function has a minimum point at x equal to 1. Example 3. Find the critical points of the function h of x equals to cos 2x minus 2 sine x. So we shall find the first derivative of h of x, so differentiating cos 2x and also differentiating minus 2 sine x. So the first derivative of this function is h prime of x equals to differentiating cos 2x using chain rule to have minus 2 sine 2x, differentiating 2 sine x to have minus 2 cos x, and then equating to 0 to have minus 2 sine x minus 2 cos x equal to 0. Therefore, factoring out, we have cos x into 2 sine x plus 1, which implies that cos x is 0, or 2 sine x plus 1 equal to 0. For case 1, we have that cos x equal to 0. Taking cos inverse, we have that x equal to 3 pi over 2, and this function is defined on the interval pi over 2, 2 pi. Hence, we have that x equals to 3 pi over 2. We know that pi is 180 degrees. That is, pi radian is 180 degrees. Case 2. For 2 sine x plus 1 equal to 0, taking plus 1 to the other side of the equation to have 2 sine x equals to minus 1, dividing through by 2 to have sine x equals to minus 1 over 2. So at this point, since sine is negative at third and fourth quadrant, hence we have that x equals to 7 pi over 6 and x equal to 11 pi over 6. Thus, the zeros of h prime are 7 pi over 6, 3 pi over 2, and 11 pi over 6. These are the critical points. Example 4. How do you find all relative extrema of the function f of x equals to minus x cubed minus 6x squared minus 9x minus 2? First, we find the derivative, the first derivative of this function f of x equals minus x cubed minus 6x squared minus 9x minus 2. Differentiating the first term to have minus 3x squared. Differentiating the second term to have minus 12x. Differentiating the third term, we have minus 9, and differentiating the fourth term to have 0. Hence, f prime of x equals to minus 3x squared minus 12x minus 9. Equating to 0 to find a critical point, and solving for x, we have that x1 equals to minus 3 and x2 equals to minus 1. So this critical point, the critical point correspond to 3 intervals. The interval 1, first interval, we have an open interval minus infinity, comma, minus 3. And then second interval, we have open interval minus 3 and minus 1. And the third interval, open interval minus 1 and positive infinity. In the first interval, we pick a value of x that is between minus infinity and minus 3 and evaluate it at f prime. At this point, picking x equals to minus 4. Minus 4 is between negative infinity and minus 3, and then evaluating f prime at minus 4 to have minus 9. And minus 9 is negative. For second interval, we pick a value of x between minus 3 and minus 1, for instance, minus 2. So at this point, f prime of minus 2 gives 3, and 3 is positive. And the third interval, we pick a value of x between minus 1 and positive infinity, and 0 is between this interval, and f prime of 0 is minus 9, and minus 9 is negative. So at this point, the first derivative changes sign twice. It goes from being negative to being positive around x equals to minus 3, which means that this critical point is a local minimum. On the other hand, it goes from being positive to being negative around point x equals minus 1, which means that this critical point is a local maximum. Applications. Minima and maxima are used in optimization problems. They include a number of constraints on resources, of which we want the best use of our resources. For example, if we want to maximize our profit given the items we can make and our available resources. Thank you. Please subscribe to my YouTube channel for more videos.